Hello, sir. Hello. Am I audible, sir? Arvind, sir?
Yes, yes, I can hear.
Yeah. Uh, so I welcome all the participants back to the session after a brief coffee break. Our upcoming speaker is Dr. Aravind H Bhashyam, Professor, Christ University, Bengaluru. The topic is some interesting design aspect of superstructural structures, Taipei 101 and Petronas towers. So I would like to request on this note to Dr. S. Kumar to brief the profile of the speaker.
Thank you, Harish. A very good afternoon to one and all. I am Dr. Kumar, Associate Professor, Department of Civil Engineering, Youth Institute of Technology, Bengaluru. It's my immense pleasure to introduce present session speaker, Dr. Aravind H Bhashyam. Professor Bhashyam obtained his bachelor degree in civil engineering from BMS College of Engineering, Bengaluru, in the year 1979. He obtained his post-graduations in structural engineering in Indian Institute of Science in 1981 and doctoral degree from Indian Institute of Science, Technology, Chennai in 1990. Professor Bhashyam started his career as a lecturer in MS Ramaiah College of Engineering in the year 1981 and in the year 1985 he joined as a project associate in IIT Madras. He has also served more than 5 years as a scientist in ACRC Madras. Around 5 years he worked as design manager in structures division, industrial and hydro, idea and riding consulting engineers, UK, New Delhi, India. More than 16 years he worked in abroad, different capacities such as project leader structural division, MSCEB in Manama, Bahrain, director structural divisions, Rain Hill, Kuala Lumpur, Malaysia, etc. In year 2011, he returned to India and served as a professor in MSRIT and professor and HOD in BMSIT, currently working as professor in civil engineering, Christ deemed to be University, Bangalore. Professor Bhashyam has published more than 30 technical papers in reputed national and international journals and conferences. He delivered expert lectures on artificial intelligence to structural engineering in University of New South Wales, Sydney, Australia, applications of finite strip method for modeling structural instability, University of Nottingham, UK, challenges in design of sky bridges of Petronas Towers, University of Technology, Malaysia. Professor Bhashyam has very vast research experience specifically on composite shear walls, interactive buckling of thin wall structures, nonlinear analysis of infill frames, nonlinear instability analysis of fiber composite plates and plated assemblies. Professor Bhashyam involved some of the remarkable projects such as Petronas Twin Towers Malaysia, worked in project management and structural division, is responsible for the redesigns and directions of Skybridge connecting Twin Tower, is also involved in the designs of underground stations and project management coordination civil structural work for the light rail transit system to Kuala Lumpur. Designed various civil structures such as barrage, intake sedimentation chamber, headrace tunnel, penstock and powerhouses in Hydal projects in Baspa. Prepared feasibility report for 400 megawatt run-off river Hydal projects which is under construction at Vishnu Prayag, UP, India for Jaiprakash Industries Limited. Designed 2.5 million tons capacity cement mill at Rewa, Madhya Pradesh, India for Jaiprakash Industries Limited. Designed and developed the knowledge-based expert system that is KBES for configuration and design of pre-standing steel lattice microwave and transmissions line tower. He also worked as consultant for BL Kashyap and Sons Company, Thornton, Thomas Etty Company, Southeast Asia, etc. He is very versatile in soft skills. He involved in the development of computer software designs coordination between various disciplines of engineering. An expert systems was developed using blackboard architecture which adopted knowledge-based systems architecture, intergraph software such MicroStation 32, Model Draft, Mica Plus, and host of other software developed in-house using Turbo C, which were used to integrate various design models. He also developed an intelligent front end for the finite element software SAP4. The knowledge was represented using frames and BBA was adopted as the fundamental problem solving paradigm. There are many more things were found in the track of achievements of Professor Aravind Bhashyam. There are very few people who identified as the pioneers both academy as well as in industry. Professor Dr. Aravind Bhashyam is the role model for young academicians and as well as industrial practitioners. Dr. Aravind sir, we are very much happy to considering our invitations and thank you for being connected with us to share your valuable thoughts and experiences. Sir, now I request you to start the session, sir.
Thank you very much. Am I able to share the screen here? Okay. So good morning to all. So basically, I'm going to discuss today some of the interesting aspects of the design of superstall structures. I would like to start with the quote from Dr. APJ Abdul Kalam. The dreams is not what you see in sleep, but the things which doesn't let you sleep. This is exactly what happened when we were constructing Petronas as well as the Taipei 101. It never allowed us to sleep, but that was one of our dreams, to have a superstall structure. So basically what I'm going to cover in this presentation is what is high-rise, what is the demand for the high-rise, development of tall structures, there are various structural loads that are acting on that, and also certain structural design challenges, what was faced by Petronas and Taipei 101. Let's understand one thing here. The structural design challenges are different for each building. It all depends upon the various parameters and also on the wind climate as well as the seismic activity and other things. So let's see what that here. So high rise as such does not have a clear definition, but this is one of the definitions of the Council of Tall Buildings and Urban Habitat that states a building whose height creates a different conditions in the design, construction, and use than those that exist in the common buildings of a certain region or a period. So we will understand as you go through that, what are the different conditions that are placed in the design as well as the construction of the tall building. Another thing that I came across while reading Tarana's book, Construction Analysis and Design of Tall Building, is that a building is considered to be tall when its structural analysis and design are in some way affected by the lateral loads, particularly the sway caused by such load. Actually, this is the main reason why the tall structure analysis and design is become a little bit complex because of this. So now, what is the demand for this high-rise building? Why do we need a high-rise building, first of all? Now, if you look at the urban areas, there's scarcity of land, especially you see in the Southeast Asia as well as in American continent, there's a scarcity of land in the urban areas. And there's more demand, that is also the demand for the business and the residential space is increasing. And this also there's a reason for the economical growth, the technological advancement that has happened. And along with that, we had the innovations in the structural system. And there's a desire to have an aesthetic in the urban skyline. And the newly established one of the concept of the city skyline, that to say that who is stronger, that kind of a thing, plus the cultural significance and the prestige that has come into this. So all these things has put an enormous demand on the high-rise building. Next, there's always a desire within the human being to build higher and higher. So that's how this demand for the high rise has started. Now, if you look at the development of these tall structures, it's not new. If you look at the Tower of Babel, Colossus of Rhodes, pyramids of Egypt, the Mayan temples of Mexico, there are many. They're all built as the symbols of power. They are the monument being protected now and are now infrequently used. But you can always classify this, uh, the development of the structure in three different categories. One, probably the period where the human aspiration started to look for something which is higher. Then we saw that economic and the social factors and the human ego and the competition started to play the role. If you really look at this, the first building, the tall building, they were built with masonry. The walls were about 5.5 feet thick. If you look at the basement wall, that is a monodrock building. That's an example, which is about 2.13 meter thick masonry wall at the ground level. It has 17 stories as such. And most of the areas were occupied by the walls here at the ground level. We had only 15% of the gross floor area, but it's a sort of a uh, human ego that plays a role here in building this thing that, yes, we have a tall building, we can build it with masonry and things like that. Next, what happens was later on, subsequently, people realized that steel could be used as a building material, and so also the concrete also came into play. But majority of the buildings that were built in the early part of the 19th and the late part of the 18th century, that were the Reliance building, the Grantley building in Buffalo, as well as the Carson Pearson Scott department stores in Chicago. And all these things were built basically with the steel structure. Now, if you look at the second period of evolution that started, basically the spurs came from the services that have been used in the tall building, like having a lift, ventilation, there, which had the limitations on the height of the building earlier because the lift couldn't go beyond a certain level. And then we didn't have such a good mechanical equipment also for the services. So once this equipment started to improve, then people realized that as we can increase the height of the building. And many corporations recognized this, and it was used as an advertising and the publicity thing for their company. And you can see that the Woolworth building, Empire State Building, they all started coming up after this evolution started. That is the area of the vertical transportation of the structure. Now you can see that this is the Woolworth building in New York, the Charlister building in New York in 1930, and then you had the Empire State Building in New York in 1931. See, all these things came up after the further technological development that came in. Then the third period, where we saw after 1950, the reinforced concrete established as its own identity, and the emphasis now shifted from architectural external dressing and the historical style, for the reasons being the functional or technological fact. So from this, you can see that the World Trade Center that came up, uh, and then you have the Sears Towers, then Petronas Towers, Taipei 101, Burj Dubai. These are all the examples of this, which served as a functional. Basically, they helped in serving certain function that was needed for this. Now, and this period also saw the transition of the structural system from a rigid frame to more efficient structural system. Then we saw the concept of channeling both the wind and the gravity load using two separate structural systems, giving them giving more flexibility to the exterior frame as well as the inner core of the wind bracing frame, and reducing the weight of the building. significantly, and that has an impact on the foundation too. So that's how the development started. And what are the things that mandate the building performance was basically based on the building integrity, the thermal comfort, the acoustic comfort, visual comfort, air quality, and the spatial comfort. So, and all these things were started playing a role. Now you see that the design and the construction of the tall tower become very complex. Now, these are some of the buildings that were happened in the third phase of the uh, development. We'll talk about it a little later. And if you see the geographical distribution of the high-rise building, initially saw that the development was in the area, was confined to the North America and maybe to certain percentage in Europe and in South America. And subsequently, a lot of development shifted towards the Asia, Southeast Asia, most of the thing. You can see that there are about 7,254 tall buildings in Hong Kong compared to 6,317 in New York. And now Singapore is also slowly catching up, now coming close to 3,700. The data that I have is a little old, and we have a lot more tall buildings coming up in the different areas of Southeast Asia. Now, what is the reason for this? Now, if you look at the various loads that comes onto the tall building, you will have the gravity load, which comes basically from dead, live, and in some cases you have the snow loads, and the lateral loads basically from the wind and the seismic load. And you do have special load cases, impact and the blast load. Now, after 7/11, the new AIC code looks at the blast load as the main requirement for the important building. So the specifications and the design criteria, they're all changing now. They're going through a different process. Now, you're all familiar with the gravity load, and the floor system accounts for the majority of this. It also depends upon the type of system that you're going to play and the type of occupancy that you have, and also the type, whether it's going to be a residential or a hotel building, and how are you going to have, whether you're going to have large spans or a short span. All those things influence the gravity load coming onto it. The other challenges that we have here in case of a tall building, which we don't normally find that in case of a low-rise structure, is that the base sizes, the quantity of the material that is required for the floor framing, regardless of the number of stories you're going to have, and also the type of frame that you're going to have, and the framing element, and the column to column height that you have, that is basically the floor height. So all these things play a major role. And how much of material are required? I'm talking in terms of material because we're talking in terms of the force, it may not have certain physical impact on this, but you not know what are the materials that get into it to resist the lateral load, and what this implication on the structural cost. And if you were to use a rigid frame system, what is this implication? And then the structural system, now what we have goes beyond the concept of the rigid frame. Now, rigid frame is not the mandatory requirement as of now. Now, based on the work of Fazlur Rahman, who's considered as the father of the tall building structures, the height, when the height of the increases beyond 10 stories, the lateral drift becomes the controlling factor of the design. And now the stiffness rather than the strength becomes the dominant factor. This is a simple example. You can see that treating the tall building as a vertical cantilever, you can see that there is an increase in the moment is almost 4 times. That is, it depends on the square of the height of your structure. So there is a premium on the height as the height of the building increases. So this is what is a very important factor when it comes to the design of the building. And the building weight and the cost, they increase in a non-linear fashion with the increase of the height. And you have to look for an efficient structural system to support that. And you also need a right kind of a material in order to reduce the weight and the cost. Now, based on the work of the Fazlur Khan, which was carried out in the early 70s or late 60s, you found that the height of the building for greater than 150 meters, it's good for a steel building. Beyond that, your lateral load start or wind load starts governing the design. And for a concrete, if the height is more than 250 meters, the wind load start to govern the design of the building. Now, once he realized, based on his work at the Skidmore, Owens and Merrill, he coined the frame that premium for height. That means you have to pay a certain amount of premium due to the increase in the height. That coming precisely due to the application of the lateral load on the structural system. So as the height of the building increases, building sway due to lateral force becomes critical, and they place a greater demand on your structural system. That means your stiffness plays a major role here. Now, this is a simple graph that was developed by Fazlur Rahman, where he compares it, based on his work, he has compared the cost for a building, a normal building. If you just consider, if you don't take the lateral system into account, it will cost about $25 per square foot. But as you go up, this was way back in 70, now it is much more. As it goes up, you find that for the same height, you start paying a much higher rate for this. Now, you understand that this comes because of the required stiffness, the lateral stiffness that is required for the building. So now, based on his work, he classified the different structural systems as a simple semi-rigid frame, as a rigid frame, frame with a shear truss, then frame with a shear band and outrigger trusses. Then he came up with the frame tube, and also with the tube in tube. And then you have the exterior frame tube. Then you had a bundled frame tube. And you also had external exterior diagonal bracing. So he classified them as type 1, type 2, type 3, and type 4 structural systems. So type 1, basically their shear frame. Type 2 will have the interacting frame, where you do have a frame, also the shear stress along with that. And the type 3 is a partial tubular system, and type 4 is a complete tubular system. So this marked the beginning of the new era of the structural evolution. You can say that in the area of the structural engineering, where you found that the whole thing underwent a change from a conceptual rigid frame to a different type of structural system. You can find more information about this in a paper published in the Architectural Science Record by Mir M. Ali of Illinois University. And then you can see that even in case of the structures which had the concrete in this, you could have a different kind of a system where you had a frame, shear wall, frame shear wall, frame tube, and tube in tube, and then you have a modular tube. So these are various structural systems that evolve over a period of time in order to see that how you can tackle the lateral load system. Now, once you understand that a lateral load system plays a very important role, now say the wind load plays a major role onto this. Probably you know, be familiar with this particular formula. QZ is equal to KV squared I, which basically tells you how the wind load varies with the height. Now, there are certain wind issues associated with the structural design. One is the structural integrity under the ultimate load, then the deflections under service load. Then the other important aspect is the building motion and the occupant comfort. Uh, this is another important thing which a structural engineer has to look into, or a wind specialist has to look into when you're coming up with the structural configuration. Even architects have to modify the design in order to accommodate these important criteria on building motion and the occupant comfort. The other important thing is the uncertainties in building structural property like stiffness and damping. And you also uncertainties in the wind loading as well as the wind climate. And there are, of course, we have the codes and the standards. They were based on the experience of it. Now we have some areas it has been modified, and now you do have computational fluid dynamics, which helps you to carry out the studies in a virtual environment, and this has also helped to a great extent in modifying this. Now, if you look at wind as such, there are different kinds of wind. One called the trade wind, seasonal winds, and the local wind. They are equally important in your design of the structure. For evaluating the wind load on the structure, what we'll make use of is the characteristics of the trade and the seasonal wind. And local winds are studied separately because they are applicable only to certain geographical location. Now, this grouping distinguishes widely from the scale of fluctuation of the wind. When you have a trade at a seasonal wind, they fluctuate over a period of several months. Then local winds, they vary every minute. So if the variations of the speed in the trade and the seasonal wind are referred to as fluctuations of the mean velocity, and the variations of the local winds around that known as gust. Now, wind flow around any object is different from the flow of the other fluids around an object. It's not steady and it fluctuates in a random fashion. Now, based on the work of Davenport, which was who carried out the work in Toronto, and you have a separate wind tunnel also to study that. Now, the University of Toronto offers a separate course in the area of wind engineering. The wind loads imposed on the building was studied statistically, and later on he carried out a lot of experiments in that area. And he said that wind force speeds are not constant; they are changing all the time. That means if I measure the wind speed now, the next minute if I measure the wind speed, it's not same as the previous one; it's different. So if you measure the wind in 1 second intervals, you often get a different measurement from second to second. And you also have extremely strong wind, that is called as a peak wind gust. Now, the gust is there for a short period of time. It increases the strength of the wind and it lasts for a few seconds. And thereafter, the strength of the wind decreases and it lasts for a few seconds. When the strength of the wind increases, we call this as a gust. When it decreases, we call this as lull. Now, what are characteristics of the wind? So we know that the wind is a complex thing, and the flow situation arises. Different kind of things, interactions can arise between the wind and the structure. So certain simplifications have to be made in order to arrive at a design wind load by distinguishing certain characteristics of the wind. That means first is your variation of wind with the velocity, next is your wind turbulence, then the statistical probability, vortex shading phenomena, and the dynamic nature of the wind. We know that wind speed is not constant, it's changing all the time. And the response of that building now depends upon the flow pattern around the building. This is complicated by the distortion of the mean wind flow or the flow separation and the vortex formation and the wake development that happens around the block body. So the large pressure fluctuation that occurs on the surface of a building due to the mainly due to the flow separation and to the vortex formation, and a large aerodynamic load are imposed onto the structural system, and this has got an intense localized fluctuating forces on the facades also. So now, under these kind of fluctuating forces, the building tends to vibrate in a rectilinear as well as in the torsional mode. So now I can classify based on the wind direction into three kind of thing. One is called the response of the building along the wind. That's called the along wind response. And the wind and the response of the building in a direction perpendicular to the flow of the wind, what is called as the crosswind response. And in addition to that, you have the twisting, that is a torsional response of the building. The along wind response of the building is mainly due to the gust wind. That is, we are assuming that the wind, which is random in nature, we can split that into a mean wind speed, and that is as considered as static. I will treat that the mean hourly wind speed as a static force acting on the structure, and the randomness is taken into account by the fluctuate, that is due to the fluctuation component of the wind, which results from the gust. So it's possible to split wind into two parts. One is the static part. Over that, I superimpose the fluctuating part of it. The large gusts that occur, it occurs for a shorter duration of this structure, and it does not affect to that extent your structure's natural frequency of, when you look at the structure's natural frequency and the gust frequency, they do not force the gust do not force the structure to respond dynamically if it acts for a shorter duration. But the larger gust, which acts for a large, the gust which acts for the larger duration, now causes the problem as it makes the structure to respond dynamically to that. So, when you separate the wind as a static and the dynamic component, the dynamic component induces the magnified dynamic load effect, which is very significant and which cannot be ignored. You don't have this problem when you have a low-rise structure, because you don't have such a high gust at that low level. So it's not a factor. It may be, yes, you design it for the static wind load, but your gust may not have it. As the height increases, the fluctuation component, that is what's called due to the eddies or the vortex that is formed, it is that puts a lot of impact on the structure, and this is handled by what's called as a dynamic response factor by the code, by all the design codes of practice. Now, there are ways to determine the fluctuating load and the wind load. I'm not getting into that, but we make an allowance for the integrity of the turbulence at the side, size reduction effects, and the dynamic amplification. The next important aspect is the crosswind response. Now, the crosswind response, that is the motion perpendicular to the wind direction, is due to the asymmetry and also due to the lateral turbulent fluctuation of the wind flow that contribute to the crosswind forces. Now, the complex nature of this crosswind loading results from the interaction of the incident turbulence, unsteady wake, and empirical and the building motion that inhibit realistic or reliable theoretical prediction. That's the reason why we have resorted to empirical way of doing things by carrying out the wind tunnel measurement based on the available, that is, the crosswind response for a tall building, it's not being subjected to interference effect. Then you also have information which knows that because of the interference effect, what are the other implications that come from it. That's the reason why it is mandatory for a tall building to carry out the wind tunnel test in order to determine the response or the wind structure response to the various forces, and thereby you alter the external surface. We'll see that a little later, how to do that in order to reduce your moment at the base. We know that the wind, the velocity varies with the height, and now the viscosity of the air reduces. Its velocity adjacent to the Earth's surface is almost zero because of the friction. This is the general nature that you see. As the height increases, the velocity also of the wind also increases. The retarding effect at the ground, that is the wind layers below, is because of the friction between your ground surface and the wind. So eventually the wind at almost at a low level becomes very small. So that's the reason why in a low-rise building, its effect is not such high as compared to the gravity load. So height at which the velocity ceases to increase, that is, becomes more or less steady, that is called the gradient height, and the corresponding velocity is called the gradient velocity. Now, when we measure the wind speed, that varies with the elevation above the mean sea level, and the averaging time level again depends upon how your code of practice has defined. Maybe standard reference is taken as the elevation of 10 meters and a standard time interval of 1 hour. So at approximately 366 meters above the ground, the wind speed is virtually unaffected by the surface friction that's across the globe, and its movement is solely dependent on the prevailing seasonal and the local wind effect. Now, the height to which the wind speed is affected by your topography is called the atmospheric boundary layer, and the wind profile within this layer is defined by the simple equation that we set at that mean wind speed at a height z above the ground is equal to Vg at a gradient wind speed, and then multiplied by z right to the power of 1 by alpha, where alpha is the power law coefficient, and z is the height above the ground. Zg again is the height of your boundary layer, which depends upon again upon your exposure. So next is your wind turbulence. As I said earlier, wind can be broken down into a simple static wind, and over that I can superimpose the dynamic nature of the wind. So when the wind is turbulent, that's what occurs when the wind flow is, the air has a low viscosity, about 1/16 that of the water. So any movement of the air at a speed greater than between 0.9 to 1.3 meters per second is bound to be turbulent, causing the particles of air to move in a random direction. So this is in contrast to the laminar flow of the particles of a heavy fluid, which moves predominantly parallel to the direction of the flow. So for the structural engineering purpose, in order to calculate our design wind load or a wind speed onto that, I can break that into mean component that is called V, and then a turbulent component. Accordingly, I can calculate the total pressure at any instant based on the relation Pt is equal to P bar plus P prime, where P bar is the average mean pressure and P prime is the instantaneous pressure fluctuation. Now, probably you would have heard about the written period in the design of the seismic load as well as the wind load. Now, written period does not mean that it's going to come back after 100 years or no. That's not the meaning of that. This is what is the probability that you have estimated something some wind load or the seismic load, what is the probability that such a huge magnitude of the load can occur in your life period of your structure? That's what we mean by the written period. So when you say that if your written period is 100 years, that a particular flood might occur in 100 years, or a particular wind typhoon can occur in 1 in 50 years. It's expressed in terms of probability. That means during the lifetime of that structure, if it is 50 years, is 1 in 100, that is 1% in any 1 year of that life. There is a possibility of this kind of a wind load being occurring. That means the next will occur about 100 years time. That means in any year, you have a 1% chance that that particular flood or a similar event can occur. So if you are to put it in a different way that a layman can understand, they say that there are 10 times less likely to occur than a flood of a written period of 10 years. So if you say the probability of 10%. So now, once you have a probabilistic approach to the wind, that where you base it on the statistical analysis. So what happens is the general expression for the probability that the design speed will be exceeded once during the exposed period of n year is given by P is equal to 1 minus PA raised to the power of n, where PA is the annual probability of being exceeded, that is reciprocal to the mean recurrence interval, and n is your number of years in experience. So now this is the probability of wind speed exceeding the design life of the building, where depend on the life of exposure, you can calculate the annual probability and mean recurrence level, and then from there you can calculate what is the probability of that wind speed being exceeded. The next phenomena that probably most of us as a structural engineer do not look into is the vortex shedding. This occurs when a fluid flow passed over a cylinder, a smooth cylinder. So this is what is there. When you get when a cylinder is smooth, you have a regular pattern of the vortices formed in the downstream. This is sometimes called as a common vortices, named after Theodore von Karman, who theoretically predicted this in year 1911. This vortice is shed alternatively clockwise or the counterclockwise from the opposite sides of the cylinder with a certain amount of frequency called f. Now, to give you a good example of that, you can see the swing of the coconut tree. When there is a wind blow onto this, you can see that coconut tree sways from one direction and then it sways back in another direction. This is exactly because of the vortex shedding that happens at this. This is an alternate pressure increase and decrease on the either side of the coconut tree that makes the wind to the tree to sway. Same thing happens with the structure too. Now, if you look at this, at a low wind speed, the shedding occurs at the same instant on the either side of the building. So it's not subjected to a long wind oscillation parallel to the wind direction. At a higher speed, these vortices are shed alternatively. So what happens is it makes the building to sway from one side to the other. So there is also an impulse along the wind direction, in addition to the impulse in the transfer direction. So how do I estimate this? It's used based on the land satellite. We have shown what you see here is the wind, the stuff cloud that is having the vortex shedding around us. This is the satellite picture. And using this, I can calculate what is the force induced, and it again depends on your stall number and the other experimental data. I'm not getting into details of all this thing, where the vortex shedding, but this is a very important aspect when you have to design a tall structure. So I can estimate what is the relationship between CD and the Reynolds number using this. And from there, I can calculate what is the coefficient and find out what is the force at that particular instant of time. And I can use the equation, the nonlinear dynamic equation, to solve that. Now, the frequency of this vortex shedding depends on the Strahl number, the frequency of and the diameter of the cylinder, and the velocity of the fluid. So this is a simple illustration of the dependency of the Strahl number on the Reynolds number. So we'll skip that. Now you see that the wind forces or excites the structure. Now your structure is not streamlined. So now what do you do? So you carry out the wind tunnel test. Now, based on the wind flow, now you can determine what is my mode shape. What is my fundamental mode shape, then the subsequent mode shape on the test. So this is an example of the wind tunnel test taken from the RWDI laboratory, and which demonstrate how the wind flow affects the motion of the structure. So, as you know, understood that crosswind plays a dominant role. So somehow you have to minimize this response of this. So one of the such things that we generally do in case of a building is to change the orientation, or you increase the setback by varying the cross-section. Bush-Dubai is an example for that. The other way of that is, we know that if I have to break the vertices, I can twist the outer exterior structure, or I can introduce the porosity into it. If I introduce the porosity into it, that means I create an opening into that. I'll allow the wind to pass through. So it does not cause much effect, whereas twisting and the tapering can also reduce your cross-twisting response. The other one, what we have adopted in Taipei 101, is the softened corners. That means the corners around that are softened so that the effect of the wind on the structure get reduced. The other way of doing that is to make the structure a tapering one, like what you see in Petronas Tower. This is an example where we carried out the wind tunnel test of this. Then we arrived at the shape of the Petronas Tower. Original shape was not like this. It was different, but based on the wind tunnel test, Cesar Pili, who is an architect of Petronas Tower, realized that we need to change the shape in order to reduce the effect of the wind on that. So the wind tunnel test helped us in arriving at the shape of the Petronas Tower. So this softening corner is basically what you have. What you do here is, in case you look at this, all the corners in a building will be sharp. That means you have a perfect 90 degree or right angle over there. Instead of it, if I can break this off into something like this, what it does is it confuses the wind around this region. So the effect of this, the wind on the building gets reduced. So you have almost 25% reduction in the base moment. And also you carry out the wind pressure on the cladding of this the tower. So that also can see that at this the curtain wall, the pressure increase on the curtain wall as it goes up. This is for a Bush-Dubai. So there are different ways by which you can do that in the wind tunnel test to see the effect of it. One such is the high frequency base force balance model. I'm not getting into all this thing because that's not the intention of it. So the next important aspect, as I mentioned earlier, is the criteria of the human response to the building motion. Now, the wind not only causes the impulse or the effect of the or impact the structural design, it also causes the buildings to move. That means the motion of the building affects the serviceability issue of your building. The commonly used criterion for the limiting the acceleration of a building upper floor is to not more than 2% of your gravity for a 10-year written period. Now, the effect of this gravity, the acceleration, that means building at the height, because of the vortex shedding that happens because of the nonlinear component of the wind flow around us, each floor tends to accelerate in that building. Now, if your acceleration is less than 0.05 meters per second square, humans cannot perceive that motion, so it's okay. From between 0.05 to zero point 0.1, people can perceive the sensitive motion. Then the object which are hung from there can sway due to this. Now, if your acceleration is between 0.1 to 0.25, majority of the people will perceive the motion, and it will affect the people working on the desk, and it will have long-term exposure, will produce motion sickness. Then if it is from 0.25 to 0.4, desk work becomes difficult, almost impossible. Ambulation is still possible, but as you go from 0.4 to 0.5, it becomes rather difficult for us, and greater than 0.85, object will begin to fall and people may be injured. So it is very important that the surface that you create for the tall structure, you have to ensure that the wind-induced acceleration is well below the perceived level. That is the level specified in the table. That's very important. So this is the criteria. So based on the peak acceleration limit, the work done by Melbourne and his researchers in the year 1989, and the earlier work done by Irwin, that is E2 curve, that was clubbed and plotted by Mendes in the year 2007. Generally, we use this curve to find out the horizontal acceleration around us. So to decide on the acceleration criteria for this. The other important aspect that is very important in case of a tall building, which may not affect your structure, but definitely affect this wind climate around the surrounding area. That is the sometimes called this as a Mary Poppins syndrome, referring to tendency of the wind to lift the pedestal literally off his feet or his or her feet. This is taken from your popular Mary Poppins movie, where you can see that Mary Poppins, once she opens up her umbrella, she starts flying. The same thing will happen if your building is not planned properly. So what happens is, in between, it creates a venturi plume, and then this creates an uplift pressure, and it makes people to fly. This is also called as a Marilyn Monroe effect to the blowing actions of women's skirt in the turbulence of the wind around the vicinity of the building. So this is the example what you see around it. Sometimes you find them walking around it. This is still, you can see that in New York, you have the same building called, that is Flareton Building, which was built in the year 1902. That was the beginning of the high-rise building, or when people started to realize that we need a high-rise building around that. So this is located in the 23rd Street at the intersection of the 5th Avenue and the Broadway. And the one vast horror that it created at the Madison Square is directly responsible for a new form of a hurricane, which meets the unsuspecting pedestrian as they reach the corner of the building, causing the extreme discomfort. They cannot cross the road. They're just being pulled back. And building by itself is safe when the wind blows from the north, but same cannot be said when about the pedestrians. They may be blown up. So due to this, now what happens is, because now that we have CFD, computational fluid dynamics. Now we can carry out a virtual investigation of this when you have a building of a particular shape and you have a building of another shape, and suppose you build a building around it, what would be the effect of that kind of a hurricane artificially created by the venturi effect of the having the building around that region. So it has become a major interest of study, what is called a pedestrian wind comfort, is a branch of wind engineering dedicated solely to study the effect of the wind on the comfort and the safety of the pedestrians and the cyclists who pass around this region. Now, it's also responsible for the urban environment and how you can control them. So this, you can figure it out when you do the wind tunnel test, when you can model that. So what you can see here, when the sheet of air moving through this, suppose I have two buildings, it passes through that, the surface, it is reluctant to rise. That what it does, it is try to force it down. This is what we call it as downdraft. And it also prefers to flow around the building rather than over it. Now, when the wind are driven into a different direction, they get deflected upward as well as downward, causing a standing vortex or a mini tornado at a sidewalk level, and they try to push the thing up. So it is very important that the pedestrians at the ground level and probably the newest thing at the terrace level needs to be evaluated. If the building is of a lower height compared to the other one, this kind of a vortex effect can uplift your roof. So we have to see that your building around that is safe. So you need to carry out the wind tunnel test on this kind of a thing. So what we need to consider here is the effect of the mechanical force of the wind as well as the thermal effect on this. Now, this is the kind of CFD study being done on this. So you can see that the pedestrian comfort, how do you assess it, whether when the person is sitting or standing or strolling, walking, or uncomfortable or exceeded, is all based on the mean wind speed. So that by carrying out this study, it's possible to evaluate what will be the speed between the two structures, and you can see at what level you are, and if it needs improvement, probably you will have to change the shape of the structure. The next lateral load that plays an important role is the seismic. So the seismic analysis and the design traditionally focused on reducing the risk on loss of life in the largest expected earthquake. That's what the thing historically, if you look at it. Now, if you look at the seismic design code, the philosophy of this code, whether you look at an American code or a Japanese code or a Chinese or a New Zealand or a Euro code, if you look at it, the philosophy of this is the building that's been designed should be able to resist a minor level of earthquake or earth ground shaking without any damage to the structure as well as the non-structural part. The second thing is it should be able to resist the design level of the earthquake ground shaking with the damage to the non-structural part, but no damage to the structural part. Now, the damage that has occurred can be repaired, and then the building can still be functional. So important aspect here is it should not cause the loss of life. And the third one is it should be able to resist the strongest earth shaking at the site without the total collapse, but potentially with extreme damage. Maybe with retrofitting and doing a little bit of repair onto this, you can bring the building back to its original state. But the building at any cost should not collapse. Now, these performance that objective that we listed out, 1, 2, and 3, form the basis of the structural design of the countless high-rise buildings world over, worldwide over. That's lasted for several decades, but this performance has rarely been verified explicitly. But this is the philosophy of the earthquake-resistant design. But the buildings have withstood this, and they have withstood this kind of a shaking. There are a lot of uncertainties associated with that. Slowly, we are figuring it out, and the codes are also changing on those lines. But none of this performance levels, or some of them probably, have been verified, but majority of them have not been explicitly verified. Next comes your deformation-based design philosophy. Now, deformation is the key parameter in the performance-based seismic design. Again, it's based on the objective listed in the previous slide. That means it should be able to resist the minor shaking or the minor earthquake without any damage to the structure or the non-structural system, should be able to resist the design shaking with a damage to the non-structural part, but the structural part should remain intact. And the third one is if it is subjected to a magnitude of the earthquake, which is beyond your design, the system or the structural system should still remain intact. It might have undergone some kind of a modification or kind of damage, but it still be functional. So when you say that, even after being damaged, it should be functional, then it becomes a question of the performance of a particular design. Say how the performance is, to what extent your building is okay with that. So this can be classified into three types: overall building movement, story drift, and inelastic deformation. So that means you allow certain amount of inelastic deformation to take place within the structure. I'll go a little faster. So now, when it comes to the design issues of it, the critical issues associated with the tall towers are the most important is the regions are prone. When the regions are prone to strong wind and the seismic effect, they should be included in your design criteria. High base overturning moment and the foundation design due to wind and seismic, high shear capacity requirement near the base due to seismic activity, high gravity stresses in the vertical elements. That means you use a high strength material to minimize the structural sizes and economical to arrive at the economic structural design, and also to maximize the net floor area. Development of the ductility in the element at the base of the structure, as well as in the other part of the structure under high compressive gravity stress, controlling the lateral acceleration, controlling the story drift, controlling the damage to permit repair, ensuring the ductile energy dissipation mechanism, preventing the brittle failures. So if you look at all these things, you see that the whole thing becomes a little complicated. Now, if you look at the Petronas task, this gives you the basic facts of it. It's completed in 1998. It has commercial offices. And now you understand that it has a commercial offices. It will have a desk inside. So people will be working inside. So we need to keep the comfort level, the acceleration of the floor level within the certain limit. So we need to ensure that the wind climate around that is within that vicinity. Now, the height of it is about 451.9 meters. The roof is at 378.6 meters, and it has the spire. That way it makes a difference. It has 88 floors, and it has 78 elevators. The cost of this is about $1.6 billion. It has now 39 elevators, that is the high-speed elevator too. They travel at 7 meters per second. So if you look at it, I just briefly go through some of the things that are key factors which change the design certain area. The engineering challenge here was to use the local available material, and you have to use a high strength material, lower tolerances than previously possible that was prescribed in Malaysia. Secondary agenda was to transfer the know-how to the developing the local industries in that. The contracting and bidding was set up by technology transfer in mind to take care that to organize the teams of the international and local firms. That means it's not purely done by the international firms. The local firm will also participate. They may not have the ideas or the experience of designing the tower, but still they should be educated. So that's how the team combination was. And the project division decided that the construction contract of the Twin Towers could be awarded to one from Japan and one from South Korea, and had divided responsibility. Now, what are the innovative engineering construction strategies we adopted? The first one, it came in the design and installation of the Sky Bridge that provided a lot, had a lot of technical challenges to the team involved in design as well as in the construction. And it had, because this is the link between the two towers, so it needed a careful design and analysis. And we had to use, the frame is built with a high strength concrete, which has never been used in Malaysian project, and technical know-how of this to be transferred. So this is a general feature of this, the plan of the whole area. We have the different buildings around, the concert hall, the KLCC retail complex, the Maxis Tower, SO Tower. There are various towers that were built before the Petronas Towers. And this is the local environment that we had in this. So it experiences a warm southeast wind, and sometimes you have very strong wind, but limited, that from October to February. Now, this is a 100-acre site for the tower complex. And then what was the problem here is that the original site that was chosen to build there had a tapering hill on which we couldn't bore into it to fix your pile. The pile will have different length. Each pile will have different length, and this will cause the differential settlement of the tower. So we had to move it to a different location, which was about 60.96 meters southwest of the original site where it was planned. Underneath that, you have a porous limestone cliff, which is dropped in elevations about 120.4 meters over the span. And its composition being limestone, it's soft, it's likely to be brittle, like to break. That was a concern. So we moved it a little to the intersection of the location where none of the piles could reach the limestone. So the estimated shift, that is, because of the shift in the foundation, that is, the savings in terms of the cost was about $20 million when we changed from one unfavorable to a favorable side. Then it also helped to resolve the traffic issues around that. You can see that the piles location, this is the cliff around it. This is how the piles were under the Cannon Hill. So we used the concrete barrette piles, and the slurry wall technique was used for up to 105 meters. And this is the kind of irregular rock that we had, and we had to build a diaphragm wall around it. It's about 2 feet 6 inches thick around that. And we had a board pile foundation around this. This is the temporary work that has to be carried out around the site to protect this and the other regions around that. So this is the architectural design of it. We can see that peripheral column around it, which is formed something like a tube-like structure. Basically, the entire architecture revolved around the sonket weaving, which is the delicacy of the wooden screen and richness of this traditional weaving methods offered inspiration for the design of the building. So this is the typical floor plan based on this. So this is how we arrive at the structural configuration. Originally, we never had this kind of a column around it. The openings, when you had a column, it was sometimes the wind shape under the wind load. You had an L-shaped corner column that would experience a biaxial bending and reduce the frame stiffness. Then columns occurred at the mid-face to obstruct the view, and also the biaxial column bending resulted in a loss of frame stiffness. We saw that here stiffness plays a very important role, so it has to be avoided. So finally, we arrived at a concept where columns are at the inset to enable the continuous uninterrupted skin to go around us. So this is how we arrived at the structural design of this. That means how we arrived at it, basically by rotating these kind of structures around that, and finally arrived at this shape. So that gives you an idea of how much work has gone in to arrive at the structural configuration. Next, it has a tapering shape around it. So the column also has to be tapered. That means it is inclined, it's not straight. So you have to see that how that could be achieved. So they are sloped inward over the 3 stories, and each tower is supported by a ring of 16 cylindrical columns placed at the inner corner, and each tower ascends and is set back 6 times. That is to reduce your wing load onto that. So this is how the whole thing looks like. You have a concrete core box here, and then you have a band of steel reinforcing tie bars around this. That is the buttle of the tower. Then you have the concrete link beam that which link the 2 columns, and they form a tube-like structures around that. And the steel beam support the floor slab, so it's a composite, typically about 4.3 inch deep concrete filling, including 2-inch metal deck. That means the deck served as the formwork initially for the casting of the slab, and it also served as a reinforcement for the slab. It was left inside the slab itself. So this is basically how this was done. And we use the concept of the outrigger. Basically, this is another structural system. Commonly, you find it everywhere when you have a boat or when you have a crane lifting a heavy equipment. Use that concept of the outrigger. Basically, these 2 legs will take onto the load. That's how the load gets transferred from here to these legs. So this was the main advantage of using it. We use a conventional outrigger and you have a virtual outrigger. Here we use the concept of a virtual outrigger to transfer the overturning moment of the core to the diagram. So this is how the outrigger truss, they transfer the force from the horizontal force that we have to get to the wind is transferred to the columns which are tied by this kind of a horizontal truss to the outrigger columns around that. So the differential throttling that can occur and the settlement between the core and the outboard does not affect your the virtual outrigger. Then you had the wind effect. So rubber sheeting and heavy galvanized anchor being put inside, this act as sort of a damper, and they sustain the vertical, the vortex shedding inside. And this is how your lateral, this inclined column transfers the load. At this, you have the concrete of a different grade as you go along from 50 to 25, and then you go up. This is how it is transferred. And then this is the analysis that is carried out in order to establish the sway between the 2 frames. They can move in a different direction. So this tower can move in one direction, this tower can move in another direction. This will cause the twisting of the bridge. So the original design was not feasible, so it has to be modified. So we converted that into a 3-hinge arch here. So this is a hinge here, and it is supported here. And this is the different facing of the construction. And this is how the outriggers between 38 and the 40th floor, they connect the core to the perimeter of the column and transfer the forces onto that. This is your sky bridge designed for the exit, which connect the 2 towers. It is an inverted V-shaped 3-hinge arch, and this basically allows the tower to move freely. That's the advantage of this. This was how the original design was as a cable supported one. So what can happen here is when this building moves in this direction, this tower moves in this direction, this building can move in opposite direction, causing the twisting. And this bridge will be subjected to enormous amount of torsion. If that, your bridge will become very heavy, and so also your foundation. So to reduce that, we have came up with the 3-hinge arch. This is how it is being connected here. This is the plan of the whole thing. And you have two mark dampers at the east sloping leg in order to dampen the structure due to in order to reduce the wind-induced excitation in the legs of the structure. So this is the plan, the elevation of the 3-hinge arch. This is the section of the arm which supports that. It's a tubular section. And this was all built in such a way and fabricated in such a way that each one is a module which can be shipped separately and brought to the site and assembled. This is how the assembly of the section being done. So I'm just going to skip this erection of this side bit. Now come to Taipei 101. The goal was to build world's tallest skyscraper, which would withstand a typhoon and an earthquake. In case of the Petronas Tower, the wind was not such a dominant one. Sorry, the seismic activity was not a dominant one, but the wind was a dominant one. Whereas in Taipei 101, both wind and the earthquake played a major important role. So the recipe that was given to us is that to build a supersized world's tallest in all proportion should have a unique shape, and it should shake well. That means it should be able to withstand the earthquake of higher magnitude and should be able to resist the typhoon and be able and serve as a financial center for the entire Southeast Asia. So this is the brief that was given to the team which was supposed to design it. So what are the challenges that we have? First is that it's the highest, it is the tallest building. It should not collapse because you see in Taiwan, it is there. If you see this whole area, this is subjected to earthquake almost every day. You can experience a minor earthquake in the zone. And also, this is subjected to typhoon, and the wind of a very high velocity will flow onto that. So this was a major challenge in the design of this tall structure. That is, you have to balance the structural need with the project demands. So the developers had the requirement, they had an architectural vision, construction constraint, and others, and this has to balance the structural need. I can see that you are always overbalanced here. You will not meet this. This was one of the biggest challenges we had. So this was built, the structural design was done by Thompson and Thomas Setti, and the architects were Lee and partners. And the construction materials used here was steel, in-situ concrete, and the cloud. This is basically the plan of the whole structure that you have. This is the office tower. You had a parking entry here. Grand Hyatt Hotel you had, World Trade Center you had here, then the City Park and a retail center. This is the main trade entrance to this. The first challenge was to height. So we needed the right kind of elevator. We needed a stable space for the mechanical, electrical, and the pumping and the fire protection risers. Then you need to come up with the economic height because the rented floor should give you, should be that the rent that you get from the floor should be more than the cost of the added floor. And because originally it was not planned to build so high, but once the Petronas Tower was built, then the people, the Taiwan Financial Center said they want to have a tallest building in the world, so they raised the height of the building. The tallest building in that region was TNC Tower in Kaohsiung, Taiwan, was 85-story. And then now with this, it became the tallest building. Second challenge was the foundation that we had. They had a soft rock beneath about 40 to 60 meters of clay and co-alluvial soil. We had a groundwater 2 meters below the ground. So we had to build a slurry wall of 1.2 meters thick to support the tower and the podium. And we single pier did not permit the bottom-up construction. So we had to resort to top-down construction. The other reason for going for top-down construction here is since the height was increased, the 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 promoters wanted that a higher moment. And so they decided to use the symbol of the Taipei, that is nothing other than your bamboo, which has 8 modules because 8 is a lucky number for them. And it's homonym with the wealth. So that's the reason why we adopted this. So it was transitioned from a lower pyramid to the upper module by highlighted by medial based on the Chinese coins. So this is how the original design was, and we made use of this bamboo, the idea from this. So, and then we arrived at this shape of this Taipei 101 that's similar to this, with a medallion here at each floor, and you can see that they're not like a bamboo. So the wind forces that is acting on it, I'm going to skip this, you're seeing that, the dynamic effect of this. So the dynamic component is causes the oscillation, the vortex shedding. So how do you conquer the wind? The typhoon of 100-year return brings about 43.3 meters per second wind gust, average over 10 minutes at a height of 10 meters. This is similar to 3-second gust of 67 meters per second of 150 miles per hour. You can imagine what is the amount of force that is exerted on this. So carried out the wind tunnel test. This is how you soften the corners of this after carrying out the wind tunnel test onto this. And once it was done, the rounded corner, now this was the base moment that was obtained in the wind tunnel test. Now, once we understood and shaped it with this, and with 1% of critical damping, you can see that the wind tunnel test is carried out. It is the first and the second and the third mount. The drop in the floor acceleration was also achieved, and also were able to reduce the design shear and the design moment in this. So this was the design criteria. The other thing that was needed is, in order to keep the building tends to sway during the wind. So we need to reduce that sway. So we have to bring in an external way or some other way of taking off the wind and the earthquake energy from the structure. So that's the reason why we went for the tune mass damper. This was designed and tested by Roman Williams and David Irwin, RWDI. And this base now we have an office in Mumbai, but this test was done in Canada, Toronto. RWDI recommendation based on this, you reduce the bending moment, torsion, static floor to floor load, appropriate load combination, and also wind-induced acceleration at the various rotation periods were tested with this. So they came up with the design of 660 metric ton mass of spherical shape, tune mass damper. The total weight, including everything, goes to about 700 tons. And various alternatives were considered in order to design this. I'm going to strip this. So we adopted a mega frame or an outrigger trusses with outrigger column, because they wanted 8 is their very favorite number. So they wanted only 8 columns to support it. So we have to design 8 super columns to support the entire tower. So this is how it is. You can see this one. These are all the 8 super columns that we have. The rest are all the other columns which come at the 8 to the So these super columns, which you see into this, they, in order to improve the lateral stiffness and the interstory drift, this was reduced. We adopted a box-shaped strap to reduce the super columns and steel box up to 90-meter level, and beyond that we had 50 to 80 thick steel plate with full penetration well around it. This is the shape of the box column, and this is the stiffener for this around it. And through this, we pass the reinforcement, so it becomes a composite. It improves the stiffness of the column, because stiffness is very important here. And this is, you can see, you can imagine now the size and the shape of the column. This is being welded around it. It's 2.4 by 3 meters by 80 thick steel plate here, especially fabricated steel plate. And this is the sequence of welding in order to prevent the warping of the plates because of that, due to preheat. Now you can see with the rebars inside and concrete to be poured. Then the other safety consideration, that what we saw in the earlier thing lies that the philosophy earthquake resistant design. So once it was done, this is the shape of the column, of the beam. That the reason why it is shaped like that is that we want the plastic hinge to be formed away from the concept here is strong column, weak beam. If there is a inelastic deformation takes place, your plastic hinges are to be formed in the beam. So that's the reason why you have a reduced cross section around this. This is based on your plastic probabilistic design. So the occupant comfort was looked into it with the inherent 1% critical damping, and the external damper that we had, that is your tune mass damper, removes that kind of a thing that happens here. So next one is to consider the strength. This is very similar to your swing that you have. Suppose I have a swing, one swing, and I have a swing at the 3 level. You can see the twisting of the swing in this case. Whereas in this swing moves freely, and again for the distribution of the load here. So that's the reason why we had the tune mass dampers, which serve both the purpose of damping the system, reducing the drift, and also absorbing the seismic energy that's been input to the system by any earthquake. So this is how it was considered. This is how the damper was placed in the 8th floor. The total weight is about 728 tons, based between 87 to 92nd floor, and it is about 18 feet in diameter. So this is how the tune mass damper. So this whole assembly is 708 tons, plus the additional 20 tons come from the supporting structure. Okay, this is very similar to your shock absorber that you have in this. This is the construction of that. So this is the tune mass damper, and you can see that how the tune mass damper oscillates when it is subjected to wind. This is the real time video of this. It was taken in 2015 on a Saturday at 8 a.m. Where there was a high typhoon which hit the structure, and the damper took all the energy. Next is your pinnacle, and this is also subjected to fatigue due to the wind. So this also has a damper inside. So while we were building, this building was hit by an earthquake. The building did not collapse, but the top floor on which was under construction had the damage. You can see the damaged part of this. This is allowed. So this was again repaired and retrofitted, and the whole building came back. And in 2004, the whole thing was inaugurated here. So what I'm trying to say here is, road to success is never straight and smooth. It requires courage and attitude to overcome the obstacles what we have. So that is the whole thing. That what APJ Abdul Kalam said, that the supreme art of a teacher is to awaken the joy in the creative expression and the knowledge of this. So thanks for the time and attention. Any questions you have, I'm willing to take on.
Thanks for an exhaustive presentation, sir. We have a couple of questions from the online participants.
Okay. Can I have the question, please?
Yeah, just a couple. Sir, can you emphasize the design criteria to overcome instability in case of high-rise structures?
What is instability you're referring to here? We are not talking about a member instability. We are talking about there's no such thing as instability here. Um, the design criteria that you have is localized. We cannot adopt what you have in IS code as 1.5 times the dead load, 1.5 times the live load, and 1.2 times the earthquake load, and things like that. First of all, you need to understand the meteorology around the space, what kind of wind or hurricane the space that has experienced it, and what kind of an earthquake that area has experienced it. So that's the reason why we went in for 1 in 200 years earthquake, because that was a massive earthquake that Taiwan has felt over a period of time. So that was the thing that was taken into account in our design criteria. And second, the typhoon that we had, um, that is the maximum wind gust that was measured, that was available. Based on that, we arrived at the criteria. So your criteria for your structural design could be different from the overall design criteria you take. See, for example, that's the reason why you carry out the wind tunnel test, that you see that with whatever factors that we have, if you look at the Eurocode, it is 1.4 times the dead load and 1.6 times the live load. That's exactly what we have in case of both Petronas as well as the Taipei 101. Then we also look at, to carry out the analysis, we also carry out the dynamic analysis in order to determine the sway due to the wind as well as due to the seismic forces. So all these things, based on that, we see that your lateral drift is within the specified limit of h by 500, and your acceleration at each floor level due to that strong wind is kept within the minimal. If with your frame alone, it can't be at the minimal. So that's the reason why you have external, that is, you have a tune mass damper which absorbs the energy and reduces the acceleration of the structure. If you don't have a unique design criteria like this, you have to see what exactly you are trying to solve, and accordingly you base your design criteria.
Sir, how to optimize the positioning of lateral load resisting systems in high-rise buildings against wind load?
Optimization is very difficult in this, but you can try. So that's the reason why you try out different structural system here. I skipped this slide because I didn't have time to do that. We tried out different alternatives based on the architectural frame that we had. See, in case of Petronas Towers, you saw how moving one square with another, we arrived at a different structural system. And that was found to be optimal in both in terms of satisfying your architectural need, also in terms of satisfying your structural need. In case of Taipei 101, we tried with a different structural system, but it has a constraint of having only 8 columns to support that. So that constraint being taken into account. So the alternative that was there was only the outrigger system. It's a bit complicated. It needs more time to explain how we arrived at that. There is no such one way of optimizing it. We have to try different system. We have to see what are your constraints to optimize it. It's taking all the criteria into account due to seismic, due to your pedestrian wind, due to your floor acceleration, meeting all this constraint, which is the best structural system, and also taking the vertical transportation system into account, and also the service flows that you need in order to house the equipment, mechanical as well as the other service equipment you need to house, because you need one floor for that. at different levels. You have the pumping station. To house that, we have to take that into account. So taking all this account, you cannot say that there is one unique way of optimizing it. We have to look into different ways of doing it.
Sir, in general practice, slab is casted for every 15 days for a high-rise structure. Can you please let us know the challenges of with respect to the maturity period of the concrete, sir, during the construction?
Regarding the material,
Maturity period of the concrete.
in case of Petronas Tower, we use self-compacting concrete. The formwork for that was a cold form steel with a different arrangement, and that served as the temporary formwork for casting the slab, and also later on it became a reinforcement for the slab. If you use, we never had the experience of at that point of time when you built a Petronas Tower using a high strength concrete. The heat of hydration that you get, you just can't stand there. Even the concrete starts cracking. So we had to get ice cube from different sources. So we requested them to send lots of ice cube in order to see that the concrete does not crack under this. So that was a problem that we had. But when it comes to the floor level, this was relatively easier, as your grade of concrete was about 40 to 50, and about in a 3 days time, it achieved a strength of almost around 25 to 30 Newton per millimeter square, as against 40, 45. So it was not a difficult thing. This technology was supplied by the Australian firm. They make this possible. Whereas in Taipei, it was totally, everything was done by either the Japanese or the South Korean firm. We never had a challenge regarding the maturity of the slab in that, because it was a little more easier in case of a Taipei 101. But it was a challenge only when it came up to the mat. In case of a Petronas Tower, we learned how to cast and how to take care of the curing with the additional thing. And it was also new to the Australian firm because the temperature was different, but we were able to overcome that using ice and other additional material to overcome this kind of a problem. Yes, you do face the heat of hydration, but maturity in terms maybe 5 to 7 days, you do get good strength of concrete.
Sir, thanks for your patient answering, and we are overwhelmed for your presence over here today for the presentation. And on the behalf of Department of Civil Engineering, Jyoti Institute of Technology, Bangalore, we really thank heartily for your presence today, and we request your continued support and presence for our future endeavors. Thanks for the session, sir. Thank you so much.
Thank you very much for giving me an opportunity to present this. Thanks a lot. Yes, you can look forward for that. Any other things you need? Yes, I'm ready, willing.
Sure, sir. Thank you so much, sir. Have a nice day. There is a announcement for the participants for the next session. It is scheduled at 2 p.m. The speaker is Dr. Kiran BV, Professor SKS-JTI, Bangalore. Topic is roller compactor cum rut analyzer, a boon or curse to design and develop quality bituminous mix. So I request all participants to have a brief lunch break and come back at 2 p.m. so that like we can witness another good lecture. Thank you.